Hi class, this is the last set of notes in Unit 3, 3.13, the Beer-Lambert law. This law is a relationship between concentration and the amount of absorbance that occurs with spectroscopy. Let's talk about it though. So getting started. It says consider the following scenarios involving solutions with color. Scenario number 1. Consider two solutions, each in a 100 milliliter beaker. One solution has a significantly higher concentration than the other one. How can you tell by the appearance which solution has a higher concentration? So if we're talking about a colored solution, which one would have a higher solution? How could you tell which one has a higher concentration? Well, a higher concentration will be darker in color, and that's the way that you would know that something was a higher concentration if it were a colored solution. Which solution absorbs more light, the higher or lower concentration? More light would be absorbed by a darker solution or a higher concentration. So if more light is being absorbed, that means it's going to appear darker in color, and that indicates a higher concentration. Important to keep that in mind. Scenario number 2, let's consider two solutions with the same concentration. This time, concentration is not what's changing, it's constant. And in the two containers with significantly different sizes. One of them may be 50 milliliters, the other one 1,000 milliliters. Just kind of try to picture that in your mind and think about what you would observe. Would the solutions appear to be the same to your eyes? Would they look like about the same darkness? Well, they wouldn't. The solution in the larger container would appear to be darker. And why is that? The explanation is here by saying which sample absorbs more light. The darker solution would absorb more light. And why is that? Well, the reason that it is because as you pass light through a larger container, more particles are going to be absorbing that light. Okay, let's look at scenario 3. And this one I'm going to do a demonstration of. Consider two solutions, one is red and one is green, and the two solutions will be tested with a red laser light and a green laser light. Which laser light is going to be absorbed more by the red solution, and how could you tell? We're going to also look at the green solution. Which color will be more absorbed by that solution? I'm going to pause the video and set up a demo and show you guys this situation. All right, this is a fairly simple demonstration that you could even do at home. All you need is some food coloring, and if you have two different colors of lasers. So that would be the one thing you maybe wouldn't have, is a green laser and a red laser pointer. But I've got a red laser pointer here, and I've got a green laser pointer. The green one is definitely brighter, but it still will serve our purpose here. I'm going to shine the red laser first of all, just at the paper, and I've got my green solution right here. And I've got a red solution, which is right here. I'm going to start with the red solution. And if I just shine my laser straight through the glass, that's what it looks like. And you can see that dot on the white piece of paper. Now I'm going to move the laser down into the red solution. And you can still see it. It might be slightly dimmer, but not really. It's about the same. Let's try it with a green solution. Again, passing through the glass, that's what it looks like. But when I move it down into the green solution, it's completely blocked. You can't see that dot anymore. Just move it right down into the green solution and it's blocked. So the red laser is not passing through the green solution. Now let's try the green laser. Again, it's a little brighter, quite a bit brighter, but there's our green laser passing through the glass and through the green solution. It goes right through. here's our red solution. It's going through the glass, and when I move it down, it's completely blocked out by the red solution. So the green laser is blocked, so to speak. It appears to be blocked by the red solution, and the red laser seems to be blocked by the green solution. So let's talk about why this is. All right, so now that you've seen that demo, which laser light is absorbed more by the red solution, and how could we tell? Well, that would be the green light. The green light was more absorbed by the red solution because the green light did not pass through a concentrated red solution to the other side. It was actually absorbed by the particles in the red solution. That is why we didn't see the light passing all the way through. The light was absorbed by the solution. Which laser light was absorbed by the green solution? Well, just the opposite. The red light was absorbed. And how could we tell? It was because the red light did not pass through a concentrated green solution to the other side. All right, so now let's talk about the Beer-Lambert law, and that is what we're relating all of this to. Sometimes we call it Beer's law for short. It allows us to correlate the factors affecting light absorbance using this equation, where A stands for absorbance. Epsilon, the Greek letter epsilon, it kind of looks like an E, but you need to know what we mean when we say epsilon values. That's molar absorptivity, which is inverse molars per centimeter. So that should be m to the -1, cm to the -1 power. B is the path length, usually in centimeters, and concentration given in molarity. So A equals absorbance equals absorptivity times the path length times the concentration. Molar absorptivity depends on the substance dissolved and the wavelength of light that is used. So how would we know which combination is best and why? Well, we want to pick the combination that gives us the highest absorbance so that we can identify the concentration of a substance. We want to be able to measure how much of that substance there is. So we want a combination that has a large amount of absorbance. So a specific substance absorbs light with a specific wavelength. We need to think about that when we pick the wavelength of light we're using. With a high molar absorptivity, varying concentration will noticeably change the amount of absorbance. That's the reasoning behind that. The path length is usually constant at 1 centimeter, and the larger the path length, the larger the absorbance. The shorter the path length, the smaller the absorbance. That's why we tend to just standardize it at 1 centimeter. It seems to be a pretty good number with most spectrometers. Okay, why is it that the longer path length gives you a larger absorbance? In a longer pathway, there will be more particles of substance that can absorb the light. You're passing through a longer path, you're going to see more particles along the way than if it were a shorter path length. That increases the absorbance. And the higher the concentration, the larger the absorbance. The lower the concentration, the smaller the absorbance. The reasoning for this is in a solution with high concentration, particles are more closely packed together. So there will be more particles of the substance that can absorb the light, and that increases the absorbance also. All right, that's it for Unit 3. You should be able to answer any questions from Unit 3 practice at this point.